marks are given by
Hello, how are you?
they will be filled in this form with your
I'll
photograph.
quickly
I will
write down who
send
you are on my
this
little list that
form.
I've here to mark,
Please
and then
you
I'll ask questions.
fix your photograph and send it to me. Okay, I will print that and make it a PDF file and uh, we will sign it and it will take time, but certificate you will get today. This is the grade exam. Means you can show it anywhere in your certificate, in your exam. That is only the degree certificate, but mark sheet is this one. Just like this, I will make there and with their photograph, this statement of grades I will put. That's why
Yeah.
I asked you.
मैंने ना इसके बाद मैं ना मतलब मेरी ट्रेनिंग चल रही है
बेटे सर्टिफिकेट तो लेना आ गया
नहीं आज तो मैं है सर अगर मेरी फोटो
नहीं ऑनलाइन
जो ऑनलाइन ही कर लो
हाँ
ये ऑनलाइन ही मिलेगा सर
नहीं ऑनलाइन होएगा बट मैं ਤੁਹਾਨੂੰ ਭੇਜਾਂਗਾ ਇੱਕ ਇੱਕ ਦਾ ਬਣਾ ਕੇ ਫਿਰ
मतलब सर सीधी पीडीएफ कटवा लीजिए बाद में
हेलो हाँ बेटा
सर मैं मतलब एक बाजू कटवा लिया ना सी क्योंकि सर मैंने लगाना है इनके मतलब मैंने फॉरेन पीएचडी करना था मुझे नहीं लगाना था कुछ ऐसा
बेटे जब तू कहेगी ਆਪਾਂ ਦੇ ਦਾਂਗੇ ਮੈਂ परसों दे दूंगा
परसों सर चलो सर फिर मैं यहाँ करूँगी मैं केपी सर ਨੂੰ ਕਹਿ ਦੂੰਗੀ ਰੋਟੀ को हैंड ओवर कर लूँगी
ਤੂੰ ਮੈਨੂੰ ਨਾ ਆਪਣਾ ਮੇਲ ਐਡਰੈਸ ਦੇ ਨਾਮ ਦੱਸ
पूनम सर
पर इतने सिग्नेचर जाएंगे 3 साल तक
चलो कोई नहीं सर फिर मैं एक दिन आ जाऊंगी मतलब मैं तुम्हें कॉल करके आ
बट आई विल सेंड इट आल्सो बाय
मेल
मनीषा ने मैडम को
ठीक है क्या है ठीक है क्या है
हाँ जी
ओके मैम
Okay. The person with the name Babita, I can't find on my list. Is there any other name I would be able to see on the form?
मतलब पास आउट है इसी साल नहीं है मतलब मई 2022 मेरी मतलब हले डिग्री नहीं आई मेरी मतलब मेरी 9.5 सीजीपीए है सर मैंने थीसिस पे डेजर्टेशन चाहिए थी सर मैंने अगे पीएचडी लिए अप्लाई करना सितंबर से सर मैं ना एक और बता दूं मैं बीसी सर्कल से रिलेटेड जा रही हूं मतलब मैं थीसिस डेजर्टेशन की हेल्प मिल सके क्योंकि अपने डिपार्टमेंट देना है
क्यों नहीं देना
सर क्योंकि मैं एमएससी की स्टूडेंट है मैंने बाहर जाके पीएचडी करनी है
मैंने 10 कहता है कि ये
थीसिस डेजर्टेशन सर
किधर वास्ते कहते हैं
सर मेरी एससीपी की रिक्वायरमेंट है तो अगर मैंने पीएचडी करनी है
वो तो तेन बनाना पड़ेगा ना
होंगी सर
एक मिनट इन्हों नाल गल कर ठीक है
Which paper would you like to talk about? Would you prefer the paper on dialysis or the paper on SARS-CoV detection? I'm not sure if I don't hear any sounds or they're not unmuting their mics. They're not unmuting their mics, so I can't hear them. There we go. Microfluidic chip. Thank you, Seema. Which microfluidic chip? The one for the derivatization or the one for the electrophoresis. Thank you. The graphitization one. What material was this chip made in?
Okay.
Does any of you know what the material was that the microfluidic device used in the derivatization paper, what that was made in? Was that a plastic glass? That's correct. Thank you, Kudip. When we look at the microfluidic design, we can see that the channel, the length of the channel has increased by using a serpentine geometry. Why did they make the channel length longer in this paper?
Extension.
Does any of you know why they used, when you look at the channel structure of the micro device used in this paper, why they used a serpentine geometry to increase the length? Let me ask that. No idea. That's clear. Do you remember, if we go from our normal scale working in the laboratory to the microfluidic scale, what happens with the flow? Do we still have turbulent flow, or do we move across to another flow regime? So, if you have a look at the paper, you can see in the image that's got the microchips, no, the second image, I think it is, you can see different reagents coming together, and you can see a color being formed when they do get together. What type of flow do you think is happening in this picture? Is it turbulent flow or laminar flow? Can any of you make a guess? Laminar flow. Thank you, Kuldeep. So we indeed have laminar flow. So if we look at that figure at numbers A and B, we can see that design has changed in B a little bit. What is the difference between A and B? And why do we see better mixing at the top of the picture? Thank you, Kuldeep. That's an excellent answer. So far, I've only received responses from Kuldeep, and he's passed the test now excellently. So well done, Kuldeep. Is there anyone else listening in with this examination? So if we've got anyone else that would like to answer a question to me, could you please let me know what the analytical technique is that is used after the chip? I think I just had Simi Gul that wants to answer a question as well. So can you find the answer in the paper? Because you're free to use the paper here. Well, the analytical technique is HPLCMS. Thank you, Sima. Can any of you give me an answer what the pump was that was used for driving the fluid transport on the paper? Yeah, Simi, what kind of pump was used? Was it a peristaltic pump or a vacuum pump? It was not a peristaltic pump, it was a syringe pump, but you've got the answer right, thank you. I think that so I've now received answers from Kuldeep, from Seema, and from Simni. I have not heard anything from any of the other people attending, so assume you're not listening in. Okay, then I assume you're doing something else. So I now have marks for Simi, for Seema, and for Kuldeep. Thank you very much for attending, and I hope it was okay to do it by Google Meets. And I hope that you enjoyed the course. Thank you. Glad you enjoyed it.
Done?
So there's more people in the meets.
Yes.
There's people that are not responding to the questions.
You did this?
So
You can give the minimum.
I've now got a mark for Kuldeep.
No, did you contacted this Jagmohan?
I've asked questions and he has not responded.
He is online?
I don't think so. I think he's got his phone on, but I don't think he's attending the exam. I think he's doing something else. Hi, how are you?
Nice meeting you. My students enjoyed your lectures.
That's great.
She's also a participant and
I
can.
also participated, but I could not do much in this part as I'm not aware of all these things.
That's
I was
fine.
busy in, just drilling my paper. Yesterday night I got the submits from the paper from molecular diversity. They accepted my paper, our paper, and we were just doing that paper. So,
अच्छा वैसे भी बंद कर देते हैं
ठीक है दूर दूर जाके चला लो
ठीक चलो
मैं वो कल कर दी मैं तेरा ना फोन ये अभी अच्छा बंद करवाना पड़ेगा बंद करवाना
Oh, we do it for here again. Let's see if I can get all the movies together. Excuse me, is it possible that I present from my own laptop? Because there's a couple of movies in there. Can I present from my own laptop? Because then I don't need to move all the... So I've got movies in there. So I've got... then I need to save all the movies in another place because they're different. So I didn't put them all in a separate folder because I thought that was useful. I'll see if I got a younger file. It's HDMI.
इसीलिए चला रहे हैं उन्हें बंद ही कर दें प्रॉपर्ली हम चार्जिंग थी फिर हाँ चार्जिंग थी छोटा चार्जिंग देख लो
So do I introduce myself or will there be a formal start? Can I just?
What do you think you want it? Otherwise, it's not needed. All are your students on.
So we're just good to go? Okay. So
You just ask.
yeah, thank you. Otherwise you're in trouble.
You can writing this very good. You can university writing. It's 266. Yes, right. Very good.
We do our best.
Yes, of course, it's because of Casey.
Yeah.
Because of the faculty is doing like good, then of course the writing.
Yeah.
If you remember, we met.
Yeah, you took us to Professor Philippe and I to the temple.
Yes. Today is one week because of the YouTube.
So Philippe is back in Germany.
Yes. They're looking great in India.
Thank you. Been treated really well. Take you shopping. Okay, so we'll wait for him, I assume.
One more tea?
I will wait one more tea. Even though we may then have to do a toilet break halfway my talk. Hi, how are you? Good. It was very good seeing you yesterday. Thanks for coming. Yeah, and I'll do, because I'm keen on the cutting shop. So I'll do a bit of reading to see what you say. Thank you. I do feel cold, but I didn't want to put my big coat over, having gone through so much effort to look blend in. And now you're all. It's easier though if you wear. As soon as I get walking and talking, you warm up. It's much harder with the cold to sit and listen.
I was reading an article in the Digest about the South Coast. So we woke up to a warm day, it was -20.
I think when I worked in Switzerland and we went up into the mountains, I've been as cold as -17 outside. That's where your skin gets tingly. When we lived in Germany last in 2017, the temperature, the whole month of January, the temperature didn't get above 0. So it was -4 during the day, -10 during the night. But the whole town was white the whole month of January. Really lovely. Everything gets really quiet because the snow dampens all the sounds. It gets really quiet. So it's really magical.
Good morning.
Good morning. How are you? Coming.
I'll be able to just spend a brief time, but I thought I should come because it's an important event. Good afternoon. Good afternoon to all of you.
Again,
Can we start? You must stand for please. For me. Honorable Vice Chancellor, sir, Professor Rosaine from Reading University, Australia, and Professor Baljeet Singh, my dear colleagues and participants. I welcome you all to this valedictory function and the valedictory lecture, which was planned on special suggestion by our Honorable Vice Chancellor, sir. And the topic is that how microfluidics can connect disciplines. By this is a multidisciplinary subject, mechanical engineering, chemical science or chemistry, physics, and biotechnology, and electronics, you can say, and electrical also. All they are merged together, and then a chip device or a sensor device is coming into existence. This is the last day of our valedictory program, and this is the last day of our Gyan program. And in this program, it was officially 9 day and 10th day is the valedictory function and the exam of the participants. All the participants, there were 54 participants all over the country. And like from Calcutta, from Uttarakhand, from Punjab, from Chandigarh, from Himachal, or from all where they participated in this program of the Gyan Network. And all the participants, they were examined today. And based on the performance of all the participants, I am happy to inform you that Ms. Poonam, she stood first in the exam.
Where is Miss Poonam?
She's there.
And
She did exceptionally well, making up this side of mathematics.
Good, unread. Okay.
thank you, sir. Now, as you know, we were discussing the Gyan program, and our Vice Chancellor is for the very short time here due to his busy schedule. So first, I would like to request him to honor our foreign expert with a Bukhari and then move into. इस सारे कोर्स के पीछे जितनी हेल्प करता है दीदी साहब ने की मैं तय दिल तो ना तो बहुत शुक्रगुजार करता अपने केमिस्ट्री डिपार्टमेंट को सारे केमिस्ट्री डिपार्टमेंट को बिकॉज many activities are going on exams, practical exams, theory exams, and so many So all the chemistry department couldn't gather here due to this examination which is going on. So for this, I request Professor Baljeet Singh ji.
हाँ जी हाँ जी सर नहीं सर
In this program, the foreign experts, Professor Hossein was the main resource person. Besides this, Professor Philip Schmidt-Coughlin, Professor Supreet Bhaga from IIT Delhi, Professor Balraj Singh, Professor Dr. Jatinder Singh Aulak, and myself, they delivered the lectures, interacted with the participants, and feedback was also taken from all the participants that will be submitted to the JAR office. And now I will request our Honorable Vice Chancellor sir to say a few words.
Well, I'm very happy that Jan program happened at the University, the Department of Chemistry. My special thanks to Professor Hossein for visiting us and bringing in a certain kind of energy into the Jan program and also into the university that we elaborate a little on that. Whatever I could gather, this program was a very specialized program, and on the other hand, it was very interdisciplinary. So, which means that to become specialized does not always mean that you become more and more confined. The program was specialized, but the approach was multidisciplinary. Now, that kind of interdisciplinary and multidisciplinary approach is very important for progress of knowledge, not just in science, in all fields. If you really see, the disciplines are created to organize our thoughts and knowledge, and the disciplinary boundaries should be useful to organize things, but should not come in the way of progress of human knowledge. That's extremely important because many times we take these boundaries a little too seriously. They are made by us, and we can always go across. So that's one thing which very clearly comes from our work, and of course that flavor you must have seen in the course also. And I think in today's special lecture, that is going to come in a much broader way because people from different departments have been invited. I already see mechanical engineers, I see physicists sitting here, so the audience is quite broad today. The second thing which I noticed is that there is a very large number of female participants in the Jan course. So it's very important because you see, the world is moving towards a world where gender equality and particularly women coming into science has to be kind of specifically encouraged because if you look at scientific research, say about 50 years ago, there were very few women. So Professor Hossein also brings in this female energy, which is now becoming prominent in science, but it has to go a long way before we see a large number of women scientists in similar positions as there are male scientists. So I think this course also puts a rate of progress in that direction that there were a larger number of women scientists, women participants, and the lead speaker also was a very prominent good scientist. What I would like to see is that how many of these women who participated in this course move towards a career trajectory in science. Because what I see is that science career is not an easy path. And there are a lot of uncertainties compared to other domains. You will be doing this and that, done a PhD and a postdoc and then waiting and then informal jobs and then families. So all this put together, sometimes it becomes very difficult for women to kind of reach where they should reach given their intrinsic talent in the field. Within India, I must tell you that there are many formal programs which help women to take up careers in science. So any of you who are interested, you can find out from the websites of Department of Science and Technology, various other institutions. So specifically, Indian scientific community is very sensitive, and it has taken proactive steps to integrate and bring more women into science. So I hope some of you will be beneficiaries of those programs and policies. Lastly, I would say that we need many more such programs. I think many more departments should write GYAN kind of proposals. It's also a matter of prestige because GYAN proposals are very highly funded in some sense. You can see from the quality of gifts that they are able to give the speakers, even to me. So it is not so easy to get a GYAN proposal. I mean, any scientist who puts together a GYAN proposal has to compete because these are well-funded programs, and that's why the funding agencies are looking for very specific, strong outcomes from these programs. And what are the expected outcomes? Expected outcomes are threefold. First, interaction. When a scientist comes and spends some time here, there will be interaction between the scientists from this institution with the visiting scientists. Next, possible collaborations. So when a scientist is here for a week or 2 weeks, interactions can lead to collaboration. And third one, the most important, the participants should be tracked. What do they do? What kind of value addition happens in their fields, in their PhD work, in their careers? So this is a threefold purpose behind GYAN. And I can see that the current GYAN course definitely, I hope, will fulfill these. From these interactions, if a collaboration emerges, that would be great. And if some of the participants take up their research problems or modify their research problems based on what they learned in the course, that would be a success of the course. So with these words, I congratulate the organizing team, specifically Professor Malik, the head of chemistry, Professor Baljeet Singh, and the whole department, which came together and put together this program. All the speakers who spoke in the program, of course, the lead speaker is right here, and she is going to give a very interesting, interdisciplinary talk, as a very briefly talk. So therefore, I should not come in the way of that interesting talk that you're going to listen to, and I wish you all the very best. Thank you. All right, so it was very nice. We met, and hopefully you'll come again.
Thank you very much.
One.
Okay, so it's, the ground is for us. Before the people are gone, it's all up to us now. So thank you very much for coming. And first I would like to acknowledge getting funding from the GYAN scheme to have the opportunity to spend 2 fantastic weeks here. I've had a great time. People walk up to me on the street, to me and Professor Philippe on the streets, helping us sightseeing around. Had great scientific interactions with people, been to birthday parties. Really, I've felt most welcome visiting Patiala University. So today I will talk a little bit on the different kinds of disciplines that my academic journey kind of linked together, my microfluidics, how that's linked. Okay, I need to stay confined. How I've linked different disciplines together doing so. And one of the things is that I really like knowing the finer detail before I draw my conclusions in science. Because if we look at the slide here, we see one picture, and based on our earlier experiences, we may draw conclusions. We see a poor little child laying out on the street. So most of us will now slowly start thinking something bad must have happened. And we only have one bit of information, we only have this picture. However, if we would have had a more complete picture, then we can see this little child learning how to ride his bike. His dad is nicely commenting on him. Then the bike drops. He gets off a little bit. And he plays an accident. None of you would have thought about this. Everybody thought this child had been poorly hit, had a bad accident, and he's just doing a game. That is the problem if you only do a chemical measurement once and not multiple times over time. A movie is great. A movie gives you a sequence of images and you get information of what's happening over time. A photograph that I showed you first only gives a snapshot, and we base our conclusions based on our earlier experiences. And the truth that has happened may actually not match whatever we've seen before. So why should we go sampling out in the field if we think a truck may have spilled some chemicals, and then take those samples to a laboratory facility to put in an HPLC-MS for chemical analysis, if we also can have a complete analytical system, a complete system for chemical analysis out in the field with us to do testing over and over again. So we get time-resolved data, like a movie provides images over time. It's a sequence of images. And Professor Andreas Mans came up with that idea in, first published in 1990, of having systems where sampling, sample transport, any necessary reactions, separation and detection are automatically carried out extremely close to the place of measurement. So rather after an incident, having to take a sample from the river into the car, through all the traffic jams, to the laboratory, do a lot of laborious processing, put all of that in a little box to take it out with you. And that field has become, initially it was named the Miniaturised Total Analysis System, and later on it's gone more broadly lab-on-a-chip research, and the foundation of everything we do in these lab-on-a-chip devices is microfluidics. One of the things that we need if we get microfluidic systems that do our complete chemical analysis workflow, one of the things that we need to do that is to achieve functional integration. For those of you that don't do a lot of chemical analysis, in chemical analysis, we first do sampling to get a small aliquot of the river water ready for our analysis. Then we need to prepare our sample so that it's actually ready. There's my mouse. So that it's actually ready and clean enough for the analysis. So we need to remove, for example, clay bits and sand from the sample. Then we need to do an assay. And the assay could be a separation, it could be an immunoassay, it could be a PCR test. There's a whole range of different chemical assays we can do, and depending on the analyte, we may pick one over the other. And then finally, we want to detect what's going on. And detection we can do with light, or we can do it with electrochemistry, with electrodes, or with very expensive instruments. So there's a whole range of options there. But if we want to do that all very close to the point where we take the sample, we need to have multiple materials and functionalities in there. If we want to use optical detection, we need to have a way to get light in there. So we need a transparent device. If we want to use an electrode to measure the conductivity, we may need a conducting material. Porous materials are really important as well for two different aspects. Porous materials are used for filtering. Maybe you've made a coffee where the coffee grinds stay behind whenever you make a coffee and you get the extract out. That is a sample preparation approach. Filtering can also be used to remove sand, and there's more advanced ways of removing particulate matter as well. If we want to do some sample preparation where we want to keep our target but remove a lot of the compounds that we're not interested in, we want to bind that to a solid support that's got a lot of surface area. Again, that is where porous materials come into play as well. So in sampling, sample preparation, but also chromatographic separations, porous materials are very important. That's why I'll be talking about initially the functional integration work that I've done on integrating electrodes in microfluidic devices. We'll do a little intermezzo looking at some neurons, and then we'll go and look at the integration of porous materials. So that will be the outline of the presentation today. In the very early days, during my PhD, we integrated contactless electrodes for conductivity detection in microfabricated devices. And the students that all attended the class know the story about this chip. It cost about 20,000 euros to make because it was very laborious. It was a 27-step microfabrication process. Unfortunately, someone had gone on holidays, not told someone to use silicon nitride for bonding, and they used silicon oxide. So very excited, in the final last year of my PhD, I received these devices. As a good dedicated person doing capillary electrophoresis, I started off conditioning my microchannels with 0.1 molar of sodium hydroxide. And the two parts of the chip came apart because the silicon oxide layer used for bonding nicely dissolved in my chemistry, which then shows that a very intimate understanding of your material science as well as the chemistry used is required by both parties. The person making the chip didn't know I was going to put sodium hydroxide in. I didn't know silicon nitride had been replaced by silicon oxide, and I could no longer use the sodium hydroxide for conditioning, simply washing my channel. The other thing that this taught me, is that expensive devices are not any good. They may provide 3 different people with a PhD, because we had a PhD student here working on the development of the detection electronics. We had one working on microfabrication, and I, as the analytical chemist, was working on getting chemical separation going. So 3 PhDs making a tiny micro device that cost a fortune and fell apart when I first tried to use it. I did got better with the second batch of devices and still got my PhD. So there was a good outcome of this, but I thought we could do this a little bit more low budget. So I developed an approach where we could actually build the same microfluidic structures on top of a printed circuit board. First, etch the electrodes, like you make any printed circuit board, did some backfilling with some photoresist, and then made microfluidic channels inside the photoresist. These devices were only about $5 each. So I significantly reduced the price with no change in functionality, no change in performance. Metal electrodes are somehow limited. So we also did a little bit of an exploration towards the use of polymer materials to work as electrodes. And here on the slide, you can see a device where we used polyaniline, a conducting polymer, as a material to form our electrodes. Polyaniline has got a great property. If you hit it with light, it melts and it loses its conducting properties. So we drop cast polyaniline on top of the surface of a glass slide. And you can see the laser here that's patterning the electrodes. Everywhere with the laser where we colored in the polyaniline, it lost its conducting properties. Everywhere where we didn't hit it with a laser, it remained conducting and it remained active as an electrode. We had great assistance here with our friends from the engineering department, because as chemists, we had no idea how to control the XY stage needed to move our substrate along under the laser. But we got some great devices out. And here you can see that we've got the devices to the electrodes to apply the high voltage to do electrophoretic separation, as well as electrodes to do conductivity detection, all integrated in a single device. I told you that porous membranes, porous materials are very important as well. So early in my PhD, we wanted to be able to get a microchip to drink from a fermenter. I did my PhD at the biotechnology department. People weren't too keen to have electrodes with high voltages inside the fermenter. So what I developed was an approach to use dielectric breakdown of the material to still get an electroosmotic flow going. So the electroosmotic flow is a surface-driven pump that you can activate by applying a potential difference over a charged surface. So if you apply potential difference over glass at the right pH, glass is negatively charged, and you create a bulk flow of liquid. So that what we did here is apply the potential difference at the sides of the electrodes, having caused dielectric breakdown at those interfaces, and that way we could generate a liquid flow from from sample to buffer here, and we could we could use it as a liquid pump to drag in the liquid from the bioreactor And here you can see your students will be able to tell you all how you do cross injection, getting the intersection filled with the analyte, and then applying the potential difference vertically. On the paper, you'll see there's a tiny green dot there of the fluorescent that's been injected, but the resolution of the projector may not be good enough to show that. A couple of years later, we revisited the idea of using the dielectric breakdown of materials to create nanopores. And here you can see a microfluidic device where we controlled the current, again, with our help of the engineers. We got a current control system to manipulate the current during a dielectric breakdown process. Depending on the pores that form during dielectric breakdown are correlated to the current that's being applied. So if we use only, there we go, a small current, 1 microamp, then we create very, very small pores. And on the images here, you can see that small inorganic ions like iron and thiocyanate can still migrate through the pores, whereas larger molecules like a fluorescent dye, in this case rhodamine 6G, cannot fit through the pores anymore because they're big. So we've created a very, very small filter. If we go up in current, we can see that we can get different levels of selectivity, where if we apply 5 microamps, we are able to just get big proteins through our pores, but we leave blood cells and other cell debris behind. So we can tune the size of our filter using the current during dielectric breakdown. And we use this to inject some samples for capillary electrophoresis, where you can see here that the transport of the analyte from whole blood into our separation channel increases with increasing concentration, and that's evidenced by the increase in peak height because we have more sample that's being injected, and we had a nice linear correlation for the concentration of quinine from whole blood. We thought we could do this any better, and we thought of creating 2 different membranes at the same time because we could create different pore sizes. So here we have membranes with 2 different pore sizes to create a trap for some molecules. The first membrane has got a relatively large size. Let's see where my mouse is. There's my mouse. There we go. So the first membrane that we've got here has got a relatively large pore size, allowing a whole range of different molecules, including our target analyte, to come through, but not the proteins. So you can see some of the balls, the red balls and the blue balls, stay behind in the reservoir up here because they are too big to fit through these holes that we've created by dielectric breakdown. The other membrane, we made much smaller pore sizes, so the small inorganic ions still could fit through, but our small molecule target analytes wouldn't. If we apply an electric field, our analytes quite happily swim out of the sample reservoir into this microchannel, and they all get stuck here because they can't get through this door. So we get a whole pileup of our analyte here, which allows us for concentration of our target analytes before separation, which is exactly what we did. And here you can see if we didn't use our size mobility trap, we hardly could see any signal. My laser pointer used to work better. There we go. So with normal injection, we just could see a quiet blur, quite a tiny little blip of the line of our fluorescent marker, but our size mobility trap allowed us to increase our analyte concentration by a factor 100, which means that we got a lot more sensitive injection, and we used this device for the detection of an antibiotic in urine, where you can see that the ampicillin has been separated nicely from other interferences, allowing us for quantification of this antibiotic from a biological sample. That was work all happening a little bit earlier on, a lot of electrophoresis, a lot of chemistry. So we changed gears a little bit and we start talking about neuroscience. Traumatic brain injury is happening with people in the boxing sport, but it's also a risk that you have whenever you are in a car accident, if your head rapidly moves forward and backward. Neurons are brain cells. And in biology, neurons are not your typical cell. They do not reproduce. So all the neurons in our head that we are born with are there for our life. We can't get any new ones. The other thing about neurons that they're quite differently depending on where you look. They've got a big cell body where a lot of the cell machinery sits, but they've got this very long axon that travels through our body to ensure the communication, to ensure we can move our arms and our legs rather than only think. So neurons are quite special cells. And in 2005, some very clever researchers realized microfluidic devices could be used to physically separate the body, the big blurby part of the neuron, from the axon, because axons really like going through small grooves, whereas the big cell simply doesn't fit in. We're talking about a channel that's 2 by 5 micron here. At around a similar time, there was also Steve Quake that thought about the Quake valve to make little pumps and do microfluidic valving. And the way he did that was by having a flexible membrane sitting over a microchannel where they could increase the air pressure. Like with inflating a balloon, whenever you apply the air pressure, you can inflate the microchannel and you get the material to bulge up, because at more pressure, PDMS is a flexible material and it gets a little bit larger. We decided to combine those two different devices, to have our micro device where we could have our axons separated from our soma, and put one of these little ballooning things underneath so we could locally injure an axon and study what was going in the whole cell. Again, with the help of our friends, the engineers, us, the microfabricating chemists, and the other friends that we recently met that worked in neuroscience, we developed this experimental setup where we needed some solenoid valves to repeatedly and reliably apply a timed pressure pulse to our little balloon to very accurately injure our axons. And after that, the neuroscientists would be able to continue with their culturing and look at the effect, the biological effects on the neuron cells. We did quantify how much the membrane deflected at different pressures being applied so that we knew how much we injured the different neurons. The thickness here, the font has changed it. The thickness of the membrane is 60 micron, not 60 millimeters. Sorry for that. So, off to work. Here we've got some neuron pictures, and the top two are when we haven't applied any injury. And if you look very carefully, you can just see mouse. Oh, that's not my laser pointer. There we go, this laser pointer. You can just see some little branches of the axon coming through. Nothing happened yet after 24 hours. After 5 hours, we can see some small blips taking place. That's where neuroscientists get really nervous, because they call it beading, and it is a sign the neuron is in serious distress. Here, we can see even more beading, and we can see that the axons start becoming segmented. They start falling apart. So we can see that over 24 hours, our neurons degenerate. So we now have a microfluidic model for studying neurodegeneration. Lovely thing about doing, it will be a little bit darker. This is a lovely fluorescence image that doesn't come up really nicely here. But we can see that when we have a healthy picture, we can see nice straight lines of the axons. Whereas if we stain them 24 hours post-injury, you can see that the red bits are a bit bloppy. Again, that is a sign of injury and the fact that these neurons, the axons, are feeling really sick. Importantly, we also looked at the cell body. So the injury was done all the way down the axon. We also looked at the cell bodies. And if you look closely, you can see the similar beading taking place at the cell body. And that means that one end of the axon actually communicates back to the cell body. We're in trouble, we're going to die. And the apoptosis process here has started. So the end of the neuron here is near. We haven't only injured one axon, we've actually injured the whole neuron by just having this tiny little 50 micron balloon being inflated on the surface where it's growing. We then came up with our next question, and this just came up as a joke over morning tea. We wondered how smart neurons actually were, and one of the questions was, can they find their way out of a maze? We were curious, but we needed a research question that was a little bit more scientifically sound as well. So we reformulated our question: can different neuron populations communicate when they're not physically in contact? And the way that we try to not get them physically in contact is to have one neuron population sitting on one side of a maze, having the maze hopefully blocking their access, having a selection of astrocytes sitting here, which are the normal bulk cells that are present in the brain, and then some other population of the neural cells here. And here you can see on the left-hand side, you can see a more close-up of our little maze where we hope that our exons would get lost. And indeed, as you can see on the picture, whenever we get our neurons to migrate through the bank, one bank is okay. By bank 3, we can see significantly fewer neurons. By the time our maze has had 8 or 9 banks, we actually can't see a single exon showing up anymore. Showing that our hypothesis that neurons are actually pretty stupid was confirmed. They can't find their way out whenever you put them in a maze. We then confirmed that we couldn't get any transport through liquid flows either. So we designed an additional microfluidic channel sitting here that we left empty, so that both the red liquid and the blue liquid would be flowing in there, and we could guarantee that there was not going to be any liquid transport from our exon population that was sitting in here, that we were going to chemically treat really badly, and the exons that were sitting on the other side. So we conducted the experiments, cultured the neurons, had the glia in there, and as you can see indicated by the arrows here, we could actually see very similar injury patterns in our neuron population at the other side as the ones where we applied the injury. So here we for the first time demonstrated that the astrocytes play a critical role in neuron-to-neuron communication. The next experiment that we did was to add a calcium chelator to see if calcium was the molecule that the cell-to-cell communication was facilitated by. And indeed, we found that in presence of a calcium chelator, our other neural population stayed perfectly healthy. So we could not only prove that which cell type was responsible for cell-to-cell communication in the brain, we could also demonstrate that the transmitter used in that system was calcium. That was a little bit of neuroscience for those in life sciences. We're back in a little bit more engineering, and the remainder of the talk will be about the great fun we've had in 3D printing. Having a couple of people with different backgrounds, we had a visitor coming in from Germany, and she was a journalist writing about 3D printing. And she excited me and a couple of colleagues about the potential of 3D printing that was rapidly developing for microfluidics. So we went to Kickstarter, which is a crowdsourcing website, and we bought one of the first MiCraft printers. So about 6-7 months later, we got this printer being delivered, and we were the first ones to actually demonstrate you can 3D print microfluidic devices and do some simple chemical tests on them. But we're rather ambitious, so just printing channels wasn't enough, because I told you before, if we really want to get to the total analysis system, if we want to do automated sampling and processing in the fields, we need to have functional integration. We need to combine porous and conducting materials. So we got another type of printer, which is called an FDM printer, that could print in 2 different materials. And we found that we had a bulk material, ABS, that a lot of people print in. And we had a second material, which was called Leyfeld. And we could, the nice thing about the Leyfeld material was that after it's exposed in water, a support material dissolves and becomes porous. So we printed our microfluidic structure. The bulk, again, here in gray, was printed in ABS. And the little yellow line here was printed during the process. We deposited, we integrated the membrane in our microfluidic device. Here we can see the Leyfeld, the filament that we bought for the FDM printer, where before exposure to water, there's no pores in there. If we've soaked it in water for 12 hours, pores with an average size of about 10-11 nanometers form. small enough for the transport of small molecules. So as chemists, we decided to try to use this micro membrane integrated device. And here you can see from the side, this is the ABS that most of the device is made of. The yellowish material here is the porous membrane. And you can see the tiny little holes, which were our microchannels that we use to add our sample and our reagents to do a chemical assay. This is how the devices look like. So we printed a whole range of different devices. We did a calibration by adding different concentration of nitrite with some zinc dust to reduce it to nitrite. And we put the grease reagents, which is a well-known chemical reagent that turns pink in presence of its target analyte nitrite. You can see that with increasing concentration of our target analyte, we get an increased amount of pink color being developed. So using some image analysis, we could correlate the intensity of the pinkness after developing after time with the concentration. We could calibrate our measurements, and we could determine the concentration of nitrate of a soil sample that we found somewhere on campus. But we're never satisfied, are we? We always want more. That's a little bit the way that we're wired up. So we got very excited when we saw 4-filament FDM printer coming up. 4 materials. Imagine, you know, my wish list was having membranes, maybe different membranes, electrodes. I want it all. So we were very pleased that we could get our hands on this printer. And then when it arrived, everybody was very excited up to the point we tried to put it together and print. Because printing with 1 material is difficult. Printing with 2 is harder because you need to align 2 nozzles. Printing with 4 different materials comes exponentially more difficult because all these 4 nozzles need to print at exactly the same location. So after 2 weeks of swearing and alignment, we got our functionally integrated device. So what we have here is a device where the black material is a conducting ABS. That provides us the electric field to do electrophoretic separations with. The transparent material is our normal transparent ABS for making the bulk of the chip. And here we have 2 different porous membranes with 2 different pore sizes. I don't have the time to show you the data now, but please remember the size mobility trap. We had big pores and small pores. With this device, we could do exactly the same experiment with that difference that we could do it a lot faster because the number of pores that we have in these porous materials was a lot larger than the couple of pores formed by dielectric breakdown. But here we've got 4 different materials that each provide a different functionality to our fluidic device, all integrated in one automated manufacturing run that didn't require any post-processing. Getting back to the porous materials, in chromatography, people have for a very long time used porous polymer monoliths as a stationary phase to do chromatography with. It is a material that's got a good solvent resilience and can withstand high pressures. We tried applying that same porous support to immobilize a ligand for palladium catalysis. So we made microreactors using exactly the same format as people used for chromatographic separations, with that difference that we used the systems not to achieve a separation, but to create new molecules. And here on the slide next to it, you can see some of these porous materials being formed in fused silica capillaries and in microchannels. And we could do it with an expensive UV lamp, as well with a UV LED system that, again, our friends the engineers had helped us brick together. Years later, so our microreactor work was in 2006. A couple of years ago was at Deakin University, and we were struggling to integrate membranes, get porous materials formed by projection 3D printing. And I thought back about making those porous materials in those monoliths. And chemically, you do that very simple. You've got monomers that form your polymer, but during polymerization, you add a solvent. This solvent doesn't participate in the reaction, and therefore it leaves holes. And those holes are that porous material. So we thought, what if we just dilute our resins that we use for 3D printing with a little bit of solvent that doesn't participate in the reaction? Can we make porous materials that way? And yes, indeed. We printed some flat sheets membranes, As you can see here, when we use a conventional hydrophilic membrane, we actually can print membranes that are sturdy if you print them 200 micron thick, and they have a pore size of about 500 to 800 nanometers. If we use a fluorinated monomer, we can also print membranes. Again, we can print them 2 layers of 100 microns, so 200 microns thick, and the pore size of this porous material was about 300 nanometers. On the image on the right, you can see that the material, the fluorinated material, was very hydrophobic. We hoped it would be super hydrophobic, but it was 1 degree in contact angle off. So we're a bit disappointed. We didn't have a super hydrophobic membrane, but we're very close. Porous materials are also good to use with bigger things than just molecules. Because those of you that don't have a background in chemistry, they start getting a little bit bored. So we start looking at some microorganisms. First, bacteria. Unfortunately, none of the bacteria survived any of these experiments because we lysed them. But very similar setup in here to our size mobility trap. We've got 2 different membranes. One we would like to have large pore size, one where we would like to have small pore size. We apply a potential difference over this chamber. Please note this chamber is really shallow as well. We like to be sensitive, so we like to have all our target analytes in a very small volume. If you move the bottom of your reservoir up, you reduce your volume that you can extract into, and you can increase the sensitivity. So here we've got our lysate. We apply potential difference. The DNA migrates through the first membrane into the extraction chamber. Then ion transport and electron transport happens through the very narrow pore size here, but those pores are too small to allow the DNA to pass. So that was our idea, to do DNA extraction. In order to optimize the process, we changed the potential difference that we applied as well as the time. In general terms, we got better sensitivity, which means lower cycles needed in PCR to be amplified. So here we've got the CQ value, which is the number of times that PCR had to cycle to get above the threshold. The lower the number of cycles, the higher the number of copies of DNA. So in this instance, lower is better. So in general, higher voltages, longer times got us to lower CQ values, but we had 2 observations. One of them is that if we applied voltages higher than 12.5 volts, we got electroosmotic pumping happening, and we emptied out one of our reservoirs, which was not quite what we wanted to do. The other thing that we saw, that our tiny little reservoir in the middle lost a significant amount of volume due to evaporation if we run our experiment longer than 20 minutes. As we're not very patient people, 20 minutes was good enough for us, so we decided to cap our time, and from an E. coli lysate, we could end up with under optimized conditions with a CQ value of 17. After optimizing the membranes, we used this for quantifying different concentrations, different cell counts of E. coli. And as you can see, when we had 10 to the 3rd E. coli cells per microliter, we could still get an amplification system with a respectable CQ value of around 28. Again, amplification time, number of cycles decreases when we had more E. coli present in our sample. So we made a very small device that facilitated the detection of E. coli, keeping in mind that the amplification here was conducted offline. Next thing we did was looking at chemotaxis. So again, we've got a membrane integrated device, and this time we wanted to look at the diffusion get a diffusion gradient of small molecules. So over time, we can see here, we put some fluorescein in our chemoattractant reservoir, and you can see the yellow dye increasingly staining down our microchannel. Our observations were that after 15 minutes, we had a good band of fluorescein of our small molecules in our chamber. After 30 to 40 minutes, we were at the middle of the reservoir. After about 45 minutes, and after about 50 minutes, actually our whole reservoir was filled with our fluorescent solutions, and we didn't have a concentration gradient anymore. So this told us that we could do chemotaxis experiments for about 40 minutes. So we put our zebrafish into the system. I hope the projector shows it well enough. So here we've got a little chamber containing our zebrafish. Once we know after 50 minutes that the food, in this case amino acid mixture, starts entering in, we lift up the reservoir and the zebrafish are freely swimming around. And here we can see that the zebrafish really like to go to the high concentration food. They're present in the top side of the chamber, and they don't really like going wandering down to the bottom of the chamber unless we get to the end of the experiment and food is present there as well. So here, expressed with a heat map, we can see that the zebrafish predominantly move towards the food source, so we can prove that there's positive migration towards the food source using this microfluidic device. That's all the information I just told you. We did the same thing with planaria, which is another small worm-like critter that lives in the mud in rivers. A very good indicator of environmental health. So we did the same thing. We had our planaria sitting in our little chamber. In this instance, we used a beef liver extract, and we wanted to see if it was the small molecules or the large molecules coming through. So you can see the little bit brownish liver extract sitting in here. All the bits of liver stayed behind in the reservoir. The small molecules diffused down. And you can see just a little planaria here swimming towards the food because he thought it sounded like all Punjab food. It smelled really good. It tasted really nice. Again, with our heat map, we can show strong positive chemotaxis towards the liver extract, demonstrating it's the small molecules in the liver extract that certainly have a chemotaxic effect on our planaria. Last thing we did is, because the devices that I just showed you were printed using a DLP printer, using a print pause print approach. Our next ambition was try to see if we could do all of this in a single process without touching the printer. So we developed the idea that we could use a grayscale mask to change the light intensity and therefore change the extent of polymerization of these polymer membranes that I've shown you in the rest of the images. And indeed, as you can see on the slide here, if we don't apply a grayscale mask, we get a dense material being formed here that just looks like a normal plastic. The higher the intensity of the grayscale mask, the lower the dosage is that this resin gets for polymerization, the larger the globules and the porous structures are that we can form. This approach allowed us to create materials with average pore sizes ranging at the low end, 50 nanometers, to the high end, 250 nanometers in pore size. So we had dynamic control by using the grayscale mask of our print speed. The way that we did that experimentally is have our DLP-based printer. So the printer works in such a way that we've got a light source sitting underneath, then an LCD screen, pretty much like your smartphone, blocking the light. And what we did, in addition to just projecting the images of what we wanted to print, is that we put a grayscale mask in between, where the white dots here don't reduce the amount of light. The darker the gray, the lower the light dose received at that location. Our print peak looked as follows. We get nice structures formed up to around 75% grayscale, at what point the polymerization is no longer complete because we no longer have the correct dosage to form our porous material. That's all good. So we use these devices to look at the different rates of wicking in the materials. We designed the devices to all have little reservoirs that we put equal amounts of liquids in, and we apply different grayscales ranging from 0% to 75% to these individual microchannels. This is how these devices look like. So you can see the start of the experiment where all of our little reservoirs were filled with fluorescing solution. And you can see the material printed under 0 grayscale was dense. There was no wicking whatsoever into this microchannel. The larger the pore size of these materials, the more porous, the easier the water wicked through. And you can see that over a set amount of time, this is after 8 hours, the further the liquid front could progress. And we got the correlation with the distance of the material wicked with the time that had been exposed. That is as we expected based on the literature, because the further you wick through a material, the larger the flow resistance, the lower the speed at which you will be wicking through. And that's the reason that these curves don't keep on going on a straight line, but they taper off a little bit. So we were very happy. We had materials that could physically obstruct the flow of liquid, of water, and therefore the transport of ions, as well as materials that would facilitate the transport of ions. So we decided to apply this to an analytical test, because by the end of the day, we are analytical chemists after all. So we took a sample, a soil sample, and put that in one of the reservoirs. Here you can see the sand from the soil still sitting in black. We put a phenanthrene, a reagent that develops an orangey color when exposed to iron, on the other side, and we watched what happened. And here you can see a series of different membranes exposed to different concentrations of iron. And you can see, as with the nitrate reaction, where we saw with the grease reagent an increase in pink intensity, the phenanthrene gets increasingly orange when there's more of our iron presence. And we could, by doing some pixel processing, we could measure the intensity of these bands, and we could get a linear correlation of the amount of iron with the color intensity that developed in our printed membrane. We were very proud here. We also had an ICP MS analysis, so a very large analytical instrument. And our quantitation capabilities from this soil sample were within 2% of the expensive instrument. So I've taken you on a big journey of microfluidics, where I told you how we've worked together with people on manufacturing, mechanical engineering, electrical engineering, and material science to develop different materials as well as experimental setups that allowed us to do a whole range of different chemical assays, experiments for the life sciences, and experiments for the medical sciences. All done by working together with people that understood the chemistry of materials and the separations or the organic synthesis. With medical people, neuroscientists, and some of the work that I haven't touched here is in clinical diagnostics, also working with medical researchers. Forensic science, some of the work I haven't been able to talk about is for the in-field detection of explosive residues, trying to trace terrorists and prevent any bomb attacks. And in food science, again, not mentioned here, but we've used our, we've developed some assays where we can do fish staining using an electric field to identify different bacteria to realize if a bacteria is going to be pathogenic or not. With this, I would like to thank my research team, and this is a recent photo where Suleiman is at the moment getting married, and he is in systems control, so his PhD is on improving the smoothness of the flow in microfluidic system. Richard is a great engineer, years of experience in microfluidics and precision machining. He operates the injection molder as well as the CNC machining equipment. I got Sumin here. Sumin is from Korea, and she does her PhD on developing new integrated cell lysis and DNA extraction protocols. Hari is about to submit his thesis. He's an Indian student that has done all the work on 3D printing of porous materials. Marci was briefly Masters of Mechanical Engineering, doing some particle separations. Dan, most brilliant postdoc, unfortunately took up an academic position in Queensland recently, and me sitting all the way in the back of my tree. Some of the work here was also done at the University of Tasmania, so I'd also like to thank the chippers and CEers there for providing a great working atmosphere. Much like to thank you for your attention. I realize I've rushed through 20 years of research in a very short time. If you've got any questions, either here or you would like to talk to me in person a little bit later on, please do so in a couple of hours I still have got. Otherwise, my email address is very well known by Professor Malik. Thank you very much for listening.
Any short questions? Yes.
Microfluidics can be cheap and needs to be fun.
So I thank Professor Hossain for introducing us to microfluidics and the combination of chemical, forensic, mechanical, and electronics in all leading to one stream, to one microchannel, and making predictions possible. So I thank Professor Hossain to come to our university for delivering this course and MHRD also. Now, before proceeding further, I would like to start the very big function, and first we would like to present token of gratitude to our resource persons and then to all the participants. First, I will request Professor Balraj Singh ji. Please. Now I request Dr. Aulat. Now, the participants, Simranjeet Kaur, Romila, Gurmeet Kaur, Romila, Gurdeep Singh, Romila, Baljesh Kumar, Akhtar Ali, Karanveer Kaur, Kiranji, Gurpreet Kaur, Shubham Chauhan, Meenakshi, Akshdeep, Kiran, Shubham Chauhan, Kavita, Arshdeep Singh, Amandeep Kaur, Kavita, Mandeep Kaur, Lakwinder Singh, Cheteshwar, Manisha, Ansar, Ritika, Sandeep Kumar, Sharu Kashyap, Manpreet Kaur,
Sandeep Kumar, Sandeep, hello,
Manpreet Kaur, Rina Yadav,
Manpreet Kaur,
Rohit Chaudhary,
Manpreet Kaur,
Rohit Chaudhary, Neha Sani, Nitesh Kumar,
Rohit,
Manish Kumar,
Nitesh, Nitesh, Nitesh,
King Shweta, King Shweta,
Manish Kumar,
Aishwarya Singh, Aishwarya Singh,
Tim Shubeta,
Kuldeep Kaur, Pooja,
Chetaswali, Pooja,
क्या नाम है?
announce it, sir. कोई और नहीं लगे। ऐश्वर्या राय, ऐश्वर्या सिंह, चतुष्वली,
पूजा, पूजा, किशनपाल, रमनप्रीत कौर, पूजा, पूजा मोर, गगनदीप कौर, सीमी गोयल, सीमी गोयल,
गगनदेव,
शालू बरफूर, बबीता, सूरज कुमार, कुलभूषण, कुलभूषण, कल्पना रावत,
और जी राम,
आनंद,
आनंद,
anyone, so thank you all of you. Please. Now I will request Professor Baljeet Singh to say a few words.
Good afternoon, everybody. Respected Dr. Hussain, Professor A.K. Malik, Professor Yusuf, and my faculty members, my colleagues, dear friends, and all the delegates, again, very good afternoon. This GAN program was in the chemistry department from 10th to 20th January 2023. In this program, several experts participated in the program. It was well organized and I congratulate the team of GAN program, especially Dr. Malik, because the whole idea was originated from Dr. Malik. And I'm very thankful to Dr. Malik because he has you see, is cumbersome to bring that kind of project in any institution or department. Of course, the credit goes to this personality, Dr. Malik, and I'm also highly thankful to MHRD, Ministry of Human Resource and Development, Government of India, for the successful completion of this course and providing all the financial help. More such programs should be organized in future. It's my personal thinking. And to Dr. Zain, for you, ma'am, I personally think that you will cherish the sweet memories of this department, our university, our campus, and of course students. I wish you all the very best, ma'am. Thank you very much, Jan.
Now, I would like to request that any of the participants would like to say something regarding the course or is there anyone feelings? Dr. Ramasan?
Respected Malik sir, Najib sir, or and our resource person, Madam Rosalie. Basically, I am a teacher from undergraduate college, PSC classes, my research is from this chemistry department. I completed my doctorate in 2002. Since then, we are not related with research. You see, my college is in Barnala, and 80% of our students from rural backgrounds. They don't know even basic chemistry and physics practicals. So we are far away from research basically. This Gyan course is really very amazing for me. As ma'am said, how she reproduced 20 years of research in these 10 days. I was not aware of these types of developments. When I learned how fluidic manipulations in channels and channels of very, very small size, very amazing for me. Then lab on chip phenomena, how entire biology and chemistry labs can be integrated on a small chip. Again, very amazing for me. And Madam Rose, she is versatile in many fields of research. Ma'am knows about biology, chemistry, mechanical engineering. You see, at that time when I did research in synthetic organic chemistry, we used to have multidisciplinary research. But our supervisors, they never, motivated for such types of ideas. We used to hide our research. We don't discuss with even in our adjacent labs the ideas. But recently we are dealing with a Star College scheme, and I am the coordinator of that scheme, in which we got some funding of 63 lakhs rupees, in which they also emphasize on multidisciplinary research. So I got ideas from ma'am. 3D printing, ma'am's ideas, and Dr. Balraj's and entire team, these young engineers. I heard about printing on simple papers. Dr. Balraj sir, they shown entire that fabrication of small code. It was really amazing. And then Another ideas of Ma'am Rosen, like these paper-based analytical devices, I can reproduce in colleges for undergraduate students. Those ideas I can reproduce. Basically, what we are giving to our students, the same electrophilic reaction, addition reaction, branching reaction, SN1, SN2, nothing else. Down practical parts, we are not including practical parts. More emphasis on the theories. But I got some ideas in the next future.